on the top of page 4, we're starting combustion reactions, which is another type of redox reaction. And so as a reminder from yesterday, when we learned about redox reactions, the way that we defined them is that there will always be a single element in the reaction somewhere. So it's going to be some element that's not part of a compound. So that would be a single element of magnesium. This is a single element of oxygen. Your diatomic elements still count as being single, but they just have a subscript of 2 because that's how they exist in nature. So in a combustion reaction, this is a specific type of redox reaction that means to burn. And really what you're going to see within the reaction itself is that a combustion reaction is any substance combining with oxygen. All products will have oxygen in them, and energy is usually released in the form of heat and light. So if you are going to tell that something is combustion, the way that you're going to see this is that O2 will be a reactant. And then for the reactions that we did yesterday, we gave little 2-word definitions. So for example, synthesis meant to make, and decomposition meant to break or to break apart. If we gave that same 2-word definition for combustion, it would be to burn. So this is what we're talking about here. So combustion means to burn. So flipping back and forth, just to kind of orient us as to where we are. So if oxygen is a reactant, that means that in every single combustion reaction, I have a single element on my reactants side, so that would make this a redox reaction as well. So having the O2, it can double count as the oxygen for combustion and also your single element to make it a redox reaction. The kind of skeleton equation for this would be like if you had element A reacting with element B in the presence of oxygen, they would react to form compound AO plus compound BO. Where oxygen is part of each of these. So this is what we're looking for to classify something as combustion. So typically you'll need a catalyst to lower the activation energy of one of these reactions, but they produce a large amount of energy as well, and so we'll show that with this little E at the end. That just means the energy is being released or produced. The fact that energy shows up on our product side shows that energy is being made. Energy is being given off by this reaction, not that it's taking energy in. So the first example that we just saw is hydrogen gas reacting with oxygen gas to form water, or it's hydrogen combusting in the presence of oxygen. So that forms water and a huge amount of energy. So that equation is already balanced for you. The next equation that we see just says burning aluminum. So when you see that word burning, in order for something to burn, it must be in the presence of oxygen. So burning tells you that this is going to be a combustion reaction. So combustion reaction, that tells you that O2 is a reactant. So in this case, if I have aluminum, aluminum is Al. Burning, that means it has to be in the presence of oxygen. So I'm going to add to that oxygen gas, which is just O2. I put the 2 on oxygen because oxygen is diatomic, but aluminum is not one of my Brinkelhoff elements, so it does not need a subscript of 2. And then in terms of what these 2 things produce, if they're going to have a reaction, that means that I start with 2 things and I end with something different or multiple different things. But in this case, if I combine aluminum and oxygen, the way that they would come together is exactly how the combination of aluminum and oxygen came together in our bonding unit as well as in our nomenclature unit. So when I put a metal with a nonmetal, I have to crisscross their oxidation numbers to write the formula. So that wouldn't just be smushing them together. I don't just push aluminum and O2 together and write AlO2. That's not how it would be written. So I would take the formula for aluminum, and if formula for oxygen, and using our periodic tables, we can look up their oxidation numbers. So remember that aluminum is right here, which would have a +3 charge according to where it is on the periodic table, and oxygen has a -2 charge. So I would have my +3 and my -2. When I crisscross them, I get Al2O3. So even though these are not the subscripts that are on my reactant side, that's okay because when aluminum and oxygen combine, that's what they will form. And then because they're not the same, that's what I need to actually balance. So there's 2 parts to this. Or I guess 3 if you include identifying what type of reaction it is. So in the equation that I actually wrote, because it's burning, I know it's a combustion reaction, and this makes it, or this means that there's oxygen as a reactant in here. This makes it combustion. It is a redox reaction as well, because in addition to the single element of oxygen, so that counts towards a redox, I also have another single element, which is aluminum in this case. So that tells me it's redox. Do you notice right away anything else that this could be classified as? It is a redox reaction. It is a combustion reaction. Does it fall into any other categories we learned about? It has one product. Okay, so what type of reaction has one product? Synthesis. Perfect. So a synthesis reaction is what we talked about yesterday, where you have 2 or more reactants coming together to form a single product. That means it's a synthesis reaction. So just one thing on your product side means it's a synthesis reaction. So in this case, I have just one thing that it's making, so that would make this synthesis as well. So this reaction can be classified as redox, combustion, and synthesis. I'm going to color code them. So redox and combustion and synthesis. And then a big part of combustion reactions is combustion of specifically hydrocarbons. So a hydrocarbon is going to be any compound that contains hydrogen and carbon. So sometimes it's just carbons and hydrogens, sometimes it's carbon and hydrogens including oxygen, so we call that a carbohydrate. But a combustion of a hydrocarbon is a special case scenario that always produces carbon dioxide and water. So these 2 things, I want you to memorize this, that carbon dioxide and water are always produced from the combustion of a hydrocarbon. So if I'm looking at this example 1, so C6H6 plus O2 yields blank and blank. I can tell that this is combustion because I have O2. And it's specifically combustion of a hydrocarbon, or combustion of a compound that contains both carbon and hydrogen. So it's going to form the same 2 products every single time. Carbon dioxide is one of those products, so that's CO2. And the other product is water, so that's H2O. And then the E at the end, that just stands for energy. So that has nothing to do with our balancing, that's just showing that this is going to put out some energy. So C6H6 plus O2 yields CO2 plus H2O. The subscripts on each side of these are different from one another, so we need to balance it, but this equation we actually already balanced, unless you want to practice it again. We already balanced it on this page, so it's the same as example G, where we had 2C6H6 plus 15O2 yields 12CO2 plus 6H2O. So we can transfer those coefficients over. So 2, 15, 12, and 6. If you need help balancing that, I already posted the video from yesterday's balancing. So you can find that one in there. This is 15, sorry. Our next example right here is burning ethanol, and the formula for this that we're using is C2H6O. So if I'm burning that, same thing happens. Burning it means that it's going to combine with oxygen. So the way that you would write this is I would take my reactant, C2H6O, plus O2, because it's burning, so that would be oxygen. And they react together to produce the same two things. This is combustion of a hydrocarbon, so what two things will they produce? Carbon dioxide and water. So same two things. It does not matter what the subscripts are here. CO2 plus H2O. So combustion of a hydrocarbon will produce carbon dioxide and water. So let's go ahead and balance this one. Carbon, hydrogen, and oxygen. I have 2 carbons on my reactant side. I have 6 hydrogens on my reactant side and 2 oxygens on my, 3 oxygens. 1, 2, 3. On my product side, I have 1 carbon, 2 hydrogens, and 1, 2, 3 oxygens. And then on one side of my equation, I have 2 carbons, and on the other side, I just have 1. So I can use a coefficient of 2 in front of CO2. 2 times 1 carbon would give me 2 carbons. 2 times 2 oxygens gives me 4 oxygens plus the 1, so that changes this to now be 5 oxygens on my product side. I have 6 hydrogens and 2 hydrogens, so what coefficient will help me and where? A 3 in front of H2O, so 3 times 2 hydrogen gives me 6. 3 times 1 oxygen gives me 3, plus the 4 that I already had. So what's 3 plus 4? 7. And I've got 2 and 2, 6 and 6, and then I have 3 and 7. What? We could try it. This one is a little bit different because I have oxygen in 2 places on this side, so we used the decimal before as our little shortcut way for this one, C6H6 and O2. We temporarily put the 7.5 there because I had only O2 on this side, and there was no oxygen in the other compound that was going to change that number, so just putting one number would actually make this perfect. But here, if I do balance this perfectly, and I put a 3.5 right here, half of 7, then I still have to add that 1, so it doesn't work out as nicely. So let's try something different. Anything else you want to change? You have an idea? Okay. Okay, if I put 4 in front of C2H6O, 4 times 2 carbons gives me 8 carbons. 4 times 6 hydrogens gives me how many hydrogens? How many is it? 4 times 6? Alright, and then 4 times 1 gives me 4 plus these two. Okay. 6. So what? Oh, it is 5. Wait, hold on. 4 times 1 gives me 4 plus 2. Right? So 6, right? Did I multiply it wrong? Oh, put a 5 there? Okay, so if I put a 5 there, 5 times 2 carbons gives me 10. 5 times 6 hydrogens gives me 30. 5 times 1 oxygen gives me 5, plus 2 gives me 7. So I have 10, 30, and 7. Okay.